Yeah, hello everyone. Today we have a talk on Celeste is NP complete, like a complexity analysis by Zeeshan and Shaanjeet. Yes.
Yeah,
Zeeshan?
yeah. Good evening, everybody. Today, Kuvar and I are going to give you a brief introduction of complexity theory required to understand the proof of Celeste being NP complete. Next slide. Computers can solve a lot of problems in a lot of ways. So, how do we decide which ones should we use? So, obviously, we'll use the algorithms which consume lesser resources. Here, resources being space and time. But how do you measure them? And how do you decide a problem is harder than other problems? This is what complexity theory answers. Complexity theory helps us determine the limits of a computational model in terms of what it can do. This creates a hierarchy among problems and models, which is referred as complexity zoo. Next slide. uh, Although the complexity zoo is quite big, it has a lot of classes. So we'll just describe a small part of it, which is quite important um, in complexity theory. That is the polynomial classes, that is P and NP. So how do we decide how we measure the amount of time a problem requires to be solved? Because multiple computers run on multiple speeds. So rather than taking seconds or milliseconds, we take the number of steps the computer takes. That is a Turing machine, which you can read upon later as the unit of time. So, P is a class of problems which require polynomial steps. Here, polynomial being a polynomial of size of input steps to solve the problem. Similarly, its counterpart, NP, which stands for non-deterministic polynomial time, which again you can read upon later, uh, is set of problems whose solutions, given a verifier and a witness, can be checked in polynomial number of steps. Now, not all of these are of the same hardness. The hardest problems in NP are the NP hard problems. So a problem A is supposed to be harder than B. If you solve problem A, you also sort of solve problem B. So what does this sort of mean? So if you are able to take a problem, convert its algorithm of solving into the problem B algorithm in polynomial time, this conversion is called a reduction mathematically. So if problem A can be reduced to problem B, then B is supposed to be harder than A. Next slide. So one of the simple examples I took from Wikipedia is reducing squaring to multiplication. So if you have a fast algorithm to square numbers with overhead of addition and subtraction and division, you can convert it into a multiplication algorithm. So this is a valid reduction because we are assuming that the operations addition, subtraction, and division take polynomial time. So as mentioned below, how you the procedure to convert squaring problem into multiplication. So then we describe the intersection of NP and NP hard. That is the hardest problems in NP as NP complete. So all the problems in NP can be reduced to these NP complete problems in polynomial time. Next slide. So there is not much use if you just classify problems into different groups without describing the relationship between their classes. So we will take an example and describe the relationship between P and NP. So far, it hasn't been. We know the problems which are P are obviously NP because if you can solve a problem in polynomial time, then you can also verify the problem in polynomial time. So P is a definite subset of NP, but the open question remains being if there is a if it is a strict subset or not. And if we find an intersection of P and NP complete, that is a problem NP complete which can be solved in polynomial time, you can use that as mentioned by reducing to solve all the problems in NP, making P and NP equal. Next please. So NP problems can be thought of as puzzles. They're hard to solve, but you can easily give away the solution. Here are the two codes supporting and not supporting the P and NP inequality. Equality. As Scott Aronson says, there won't be any creative leaps if P was NP. That is, finding an algorithm to solve and checking if the algorithm was correct would have the same value, which we see that it's not true. And then, uh, what if there is a simple way and we just do not know or understand it so far? Next slide. So one of the examples of NP problems is Sudoku. You can solving a Sudoku is hard, but like if once it's solved, it's pretty easy to verify. So a Sudoku belongs to NP, but so far we do not know if it belongs to P. Next slide. So now we'll prove that Celeste is NP complete by a reduction method. But before that, we are going to describe you the mechanics of the game. So uh, mostly the game has just three mechanics, that is movement. The player can move in eight directions with a jump. There is a dash which grants the player, that is Madeline, extra momentum to reach platforms which she couldn't reach with the jump. As you can see in the dash, her hair color changes from red to blue. When the color changes, she cannot dash anymore until it recharges. That is when she hits the ground, as you can see. And the last one being a simple wall grab, but with limited stamina, after which she'll start falling down. This is the game mechanics. Next. So they are combining these three mechanics and a lot of objects in the game. The game is made hard. So one of these are the three objects we are going to use in our proof. That is the door. As you can see, when Madeline dashes into the button, the door opens, and once you dash into it, the door cannot be closed back because the button is now embedded in the platform. And the other one being the unstable platform, upon which if you stand for a long time, the platform will break, but after it breaks, it reforms back on top of it. So, and the most important part being that that platform cannot be broken from the bottom, making it a one-way trap. So you fall into it once, you cannot go back up. And the last one being space block, which is pretty aesthetically pleasing to look at. So this object, when you dash into it, it will take you into a straight line to the other side of the block without letting you control the player. So it makes the player travel into a straight line, and if there is a wall on the other side of the platform, the player will just die and respawn. So these were the game mechanics. Now Kuer will explain the proof.
Okay, we'll move on to the theoretical parts of the proof, and we discuss the mechanics. So first, there is a very easy part of the proof that Celeste is NP. So to prove this, we just need to show that if we have we can provide a polynomial time solution, and we can check that in polynomial time. So that is very easy to provide. We can give a solution that here is a pathway, you can follow that and reach the end. Oh, sorry. So one thing, when we say that Celeste is NP complete or NP, or Celeste belongs to X complexity class, we mean that the problem of the problem of determining whether we can reach from start to end in a Celeste level, that problem is NP or uh, hard to decide, whatever. Where, want to clarify this again? When we say Celeste is in X complexity class, we mean that the problem of checking if there exists a pathway or a solution from start to end in a Celeste level, that is the problem we are talking about. So to prove that Celeste is NP, we just need to provide a polynomial time solution that here is the pathway, you can follow this, and you can check that we can reach from start to end. So we have the we have to prove two things, that we can check this in polynomial time and the pathway is polynomial. The thing about checking if the pathway is polynomial size, we can say that we can check in polynomial time by just mimicking those moves, and we can do that in polynomial time. But we also have to prove that the number of moves is polynomial. uh, that I think that can be proven, but that is very going into very details, but I'll still tell you. So once we open a door, we track the game by doors. Let's say there are n doors. Once we opened, let's say x doors, between the x door and x plus 1th door, there is a polynomial number of moves. Otherwise, you'll be stuck in a cycle. And since we are showing a solution, we can cut that cycle in between and just have a solution that uh, between going to gates, you will have a polynomial number of moves. So this proves that Celeste is NP. Now we will build a framework. So first I will, to build a framework, I'll just tell you about the 3-sat problem. So 3-sat problem is that we are given an expression. The expression works like this. This is called a literal x1, x2, not of x3, x2, x3, x1. These are Boolean variables. So x1 can take value 1 or 0. Not of x3 means if x3 takes value 1, then not of x3 takes value 0. This is a basic Boolean algebra. So what does this mean? That this is a clause of which contains OR of 3 variables, and the clause is just defined as OR of 3 variables, and the this expression will be AND of clauses. Many clauses, you will have n variables something. So the problem 3-sat is given an expression 3. This is called a 3CNF form, 3 conjugative normal form. You have 3 variables in each clause, and the problem 3-sat is can you satisfy this expression, which means can you give a configuration of variables. Configuration means we set x1 to 1, x2 to 0, or x3 to something. Does there exist a configuration such that this expression evaluates to true? This has been proved to be NP complete. Now the proof is not related to what we'll do, but I will share resources later where you can check that the 3-sat problem is NP complete. But we will use the result that 3-sat is NP complete to prove that the Celeste, again the problem of finding from start to end, does there exist a solution, is NP complete. To do that, we will build a framework. So first we'll show how to reduce this framework. Given that we have a framework, we reduce this to 3-sat. If we were able to reduce this to 3-sat, then we know that this framework, the problem of satisfying this framework, is NP hard. So if we can build this framework using Celeste, then we have proved that Celeste is reducible to 3-sat, which means Celeste is NP hard. So I'll show how this framework, or whatever this is, can be reduced to 3-sat. So this framework was studied by us from Eric Demaine's paper. Here is the link. I will have shared this under resources. So there are like 5 gadgets in this. Start and finish. Start and finish are just you spawn here, and once you reach finish, the game ends. This is a very simplified math. You could say very simplified game. You start at start, you follow lines, and you end at finish. So this is a gadget. Okay, and the variable. Yes.
One question.
Yeah.
So you want to show it's NP hard, right? So
Yeah.
you have to. Don't you have to show that
Oh,
3-sat
sorry.
reduces to this framework?
Yeah. We will show that 3-sat reduces to this framework and then show how to build Celeste using this framework. I'm very sorry. So we will have a start gadget, again finish, and the variable gadget. I'll describe the variable gadget. It allows you to make a choice. Either you choose X or you choose not of X, which means either you set X to true or you set X to false. This is what the variable does. Variable gadget. Once you make a choice, you cannot go back. It works like this. Once you make a choice, once you choose X is equal to true, you cannot choose X is also false. So this is what a variable gadget does. Now a clause gadget has 3 literals or variables, not variable gadgets. It has variables. It is connected to a variable. Like it has, if this variable was X, the clause is connected X. Clause had X, so it is connected to this. This clause has X, so it is connected to this variable. So if we set X to true, we can travel to this and unlock this whole clause. So if any of the variables we travel through this, we unlock the clause. Once we unlock the clause, in the end, we will just travel through this. If all the clauses are unlocked, we will be able to reach finish. If any one of the clause is not unlocked, we will be stuck there, and the problem of finding a pathway from start to finish is not satisfied. But if we were able to unlock all the clauses, then we will be able to reach finish. So this is very similar. Now there are more details of it. Now we have start to finish, which I described. A variable gadget forces a player to make a binary choice. Either you set x to true, which will indicate by x. This just means you set x to true or not of x to true, which means you set x to false. So this is what you can do using a variable gadget. A clause is just like if you choose x, then you can unlock these and then you move on to the next variable. You set x, you set all the clauses with x as unlocked, and then you move on to the variable y, and you do the same for y. You move on to z, and then you do the same thing for z, and then you move on to the check phase. Now in the check phase, what you do is you traverse through all the clauses. If all the clauses are unlocked, then you can travel through it. Now this is a very simple reduction of 3SAT to this framework. What you did was you set x or x naught as true. You converted each clause. Here is the clause, whatever you had these ors, and you have this variable frames. You can variable gadget, you can set x or whatever, and if all of them are satisfied, then you can find a pathway from start to finish. This is, if you can find a pathway from start to finish, then you can satisfy this clause. This is how it reduces 3SAT to this problem. There is also another very small detail, crossover gadget. The crossover gadget allows passage via two pathways that cross each other. Since we are talking about 2D games, like these two pathways can cross each other. So how do we travel? How do we ensure that if we are going in this direction, that we do not go in this direction? So to do this, we create a crossover gadget which does this. If you're coming from here, you can only go here. And if you're coming from here, you can only go here. We'll show how we'll build the crossover gadget. So are there any doubts how we reduce 3SAT to this? I'm not really sure. Does any part need more explanation? Please ask.
Can you explain the crossover? What the problem was there?
Okay, so this is a 2D game, right? We cannot just jump from here some like this and go here. What if I want to ensure, let's say x naught was some way crossing to this. Now I don't want, if I set x as true, I don't want to set not of x as true, as it is automatically false, right? So if I choose x, and let's say this was crossing some way here. Can I draw here? Okay, no. Did I mess up? How do you how do you fix it? Hello?
Yeah, you're audible.
Yeah. How do you fix this?
Yeah, it's visible.
Okay. Yes, so about the crossover gadget. Let's say you set x to true. You do not want not of x to be set true, as it is already set to false. So let's say there was a pathway coming to here. Now, if you set this to x, and since this is a 2D game, you may be able to travel here, right? Since you cannot just jump out and uh, go here. You cannot overlap two lines, right? So since you want to prevent flow from one pathway to other, so use crossover gadgets. Like you are at x, you want it to go to here only. You do not want it to pass from here. Is that does that explain it?
Yeah.
Okay, so these were all the gadgets. So this is how we reduce 3SAT to this framework. Now if we can build this framework using Celeste, then we have essentially showed a reduction from 3SAT to Celeste. The problem of finding, if the problem of checking if there exists a solution from start to finish. So once we have shown that this problem is NP hard, we also showed that the problem is NP. Thus the problem is NP complete. Now we'll show how to make these gadgets and build this game. Zeeshan?
Yeah. So first we construct the variable frame, that is Once the player makes a choice between true or false, the player should not be able to reverse its choice. So what we use, as we showed before, the unstable platform cannot be broken from below. Once you choose true or false, the platform will reform, hence sealing your choice. So in this way, we construct the variable gadget, where one frame is there is one frame for one variable. So if there are n variables, there are only n frames, keeping it still polynomial and making the choice permanent. Yeah, next slide. Now, suppose we want to OR three frames, sorry, or three variables. So that means even if one of them is true, then the expression evaluates into true. So out of these three doors, even if one door was open, we could go from the left side to the right side. So there are three buttons which we will show how they're reached. Each button opens one of the doors as marked by numbers. So if at least one of the buttons is pressed, that means this clause will be evaluated as true, and you will be able to go from left to right side. So this is the clause gadget. So as Kuvar mentioned that you cannot have jumps in 2D games. How do you prevent path leakage? That is, suppose the player is in the path of B1 to B2. How do we stop the player from going from B1 to, like, let's say, A1 or A2, or the other way around? So what we do is, if you remember space block, we use space block. Space block forces the player to move in a straight line, and if the player tries to make some angle here, the player will just die because they'll hit the wall. The angle between them is more than 45 degrees, and the player cannot make more than 8 directions of movement. So if the player is at B1, the only place the player can move is to B2. If they try any other angle, they'll just hit a wall and die. So this is a crossover gadget. Next. Yeah. So now our variable frames, we have to connect them to the
Oh, one
buttons.
second. This is not a gadget in the framework. This is us showing how you connect the variable frames to the clause gadgets, how you activate the clause gadgets from the variable gadget.
Yeah. So now suppose the player chooses x1 to be true. Now these buttons are in line, in sequence. We want them to press only the button corresponding to x1. So we put that space block there. Now that is the crossover frame. Now the player can only move in the straight line, go up, press the button, come down. And now when they move forward, they cannot access other buttons, because if they try to do so, they'll just hit a wall and die. So this means if a player is in X1 tunnel, the only buttons they can access are the buttons corresponding to the X1 variable in the clause. So the tunnels are kept away from leakage into other tunnels. Next slide. So now, how does the game work? So first, you spawn at no, go back.
Okay. No, I was going to show.
Yeah. So we spawn at x1, we chose a value for it, pass through the tunnel, and then end up at the starting point of x2. We repeat this until uh, we end up at the last variable. That is, you start at x1, you press the button, come down, go cover all the path, and drop from the top of x2. Now, what happens when you reach the last variable? Where do you go from there? Next slide. So, for the example of three variables, suppose we reach x3, and we want to make a decision, that is x3 is true or it's false. Now, once you cover the path, that is the tunnel, make the decisions, you drop in this final passage, which on one end you drop, there are or clauses in between, and then the other end leads a pathway to the flag, which is the endpoint. So, if at least one door in each clause, that is, or of the three variables, is true, that is, at least one door is open, they can go through all of them and they can reach the flag. But even if one of them is closed among all the three for a clause, all of them are closed. That means none of the variables satisfied that clause. Hence, the doors are closed. Hence, preventing you from access to the flag. Uh, 1 minute, go back. Since we consider, let's suppose there are m clauses, there will only be m of these frames, keeping it polynomial. Next. So for the formula x1 or x2, not x3, and not x1 or x2 or x3, that is the given formula, we construct this big level. This might seem hard to follow because it's pretty messed up, but we'll give you an example of substitution of this and how the traversal happens. Yeah. So, for example, let's consider this substitution, that is x1 equal to 1, x2 equal to 0, x3 equal to 1. Now, suppose we chose x1 as 1. So that is we choose the true. So the true one as given, the first literal in the formula is x1. So x1 when chosen true should have access to that button. So the player goes, presses the button, that will activate that door, opening it, and then the player continues their path from this through the tunnel, going up and then dropping at x2. Next slide. Now we chose x2 as false, and there is no literal of not x2 in the formula. That means x2 choosing false should not open any door. So that is visible. Like the player has to just move straight, pass through all the space blocks, that is the crossover gadgets, and end up at x3 as seen as in the red line. Yeah, next slide. Now, finally, we choose x3 as 1. The last literal in the formula is x3. So, the player gets to open one more door. The player opens the door, hence opening one door in the second clause. And they end up in the final passage. Now, next slide. Yeah, now there is at least one frame open in each set of three doors. So the player can access the end flag. And as expected, substituting 101 in the formula will evaluate the formula into true. And in the level, the player gets access to the flag. So the player getting access to the flag corresponds to the formula getting evaluated as true, hence showing that we can reduce 3sat into a level of Celeste. So this is a specific construction for this level, but this can be generalized into any formula, and the frames will still remain polynomial because n frames correspond to n variables correspond to n boolean frames, m clauses correspond to m uh, or clause frames, and there are only some polynomial of m and n frames for connecting, such as the crossover gadget or the flag frame. So this proves that Celeste is as hard as 3sat. That is, if you are able to find an algorithm to solve Celeste in polynomial time, you can also use it to solve 3sat, making it NP hard. And as mentioned in the starting by Coover, that Celeste is also NP because given a path, you can check if the path is correct or not, making it NP and NP hard, which makes it an NP complete puzzle. Now, Coover will explain that how making a small change into this game will make it a P-Space complete game, and why that small change made it P-Space complete.
Could you go back to the level? Yeah. Could you like re-explain what the space blocks are doing in that? Yeah.
Oh,
Yeah.
so Zeeshan,
Okay. You want to do it or should I do it?
you
Yeah, okay. So suppose the player takes x1. Now the space blocks, what they do is they make you move in a straight line make you move in a straight line without getting any control over Madeline. So what the space blocks do is they prevent uh, you from accessing other buttons from one tunnel, or even preventing access of other tunnels from one tunnel. So suppose in the formula only the first variable is x1, the rest aren't x1. So the space blocks ensure that the player, if they take the true path in x1, they only get access to the true button, that is the first literal button, and the rest they just have to pass through it, they won't get access to the buttons. Does that explain what space blocks do?
Yeah. So I'm just looking at this example because like the lengths are confusing
Yeah,
me.
yeah, the thing is, wherever there is a space block, assume it to be the one shown in the crossover
yeah, it's just
gadget.
a crossover gadget. It forces you to travel forward. Like from
So
here,
it's
you
not drawn to scale.
yeah.
Okay, cool.
Uh, Okay, now we'll talk about what first PSPACE is, what is PSPACE completeness versus what is PSPACE hardness. And I'll mostly assume that you know what PSPACE is, but I'll try my best. If a decision problem is in PSPACE, that means it uses polynomial amount of space. Uh, uh, that is what the definition of PSPACE is. And if every problem, if a problem is in PSPACE, uh, no, sorry. If every problem in PSPACE can be reduced to another problem, then that problem is another meaning as a particular problem, then that problem is called PSPACE hard, uh, which means that every problem can be reduced to that problem. If a problem is in PSPACE as well as is PSPACE hard, then it is called PSPACE complete. So this just means that PSPACE complete are the hardest problems in PSPACE. Uh, Also, there is a theorem called Savit's theorem, which proves that by getting non-deterministic uh, amount of space, non-deterministic space, you do not increase the power of p-space. So this just means that p-space is equal to np-space. That this will be useful as you can just verify that you can have a verifier that works in polynomial space and still say that it is in p-space. This is useful later. So additional features that will add to Celeste is now instead before we could, when we pressed a closing, when we pressed a open button, the door opened. Now we add a new feature, which is if now there is a red button which closes the door. So how it works is when the door is open, the red button is deflated. So you click the green button and the red button pops out and the door opens. Similar thing you do for red button, you hop on the red button, green button pops out and the door closes. So similar to the previous approach, we'll show a framework such that this framework can be reduced to the TQBF problem, true quantified Boolean formula. Uh, uh, this is a, I'll tell what it is. This is known to be a PSPACE complete problem. There is a proper proof for it, which I will share after because it's very long. I will not show here. So TQFB problem is that you are given what do you say, a Boolean expression as before, a 3-sat like expression. Okay, but now instead of just giving a configuration, you will also have quantifiers in front. Quantifiers like there exists x for all y. With the same expression, you have there exists x for all y, there exists z, and such. So you have to check uh, for a expression with these quantifiers, does this expression always evaluate to true? Now this is the TQBF problem. This problem is known to be PSPACE complete. So we'll show how to reduce the TQBF problem to this framework, and then we'll show how to build this framework using Celeste. This framework is again based on that paper we used, we shared, and we'll also share afterwards, I guess. So in this is simpler, this is a bit easier to understand. Now there are 4 gadgets: start, finish. As before, you start at start, end at finish. Celeste is still the problem of Celeste being in complexity class is still same. Does there exist a path from start to finish? Okay, so now we have a 4 gadgets: start, finish, same. Spawn point, end point. Clause still remains same. You have let's say a 3 variable for or 3 or of 3 variables, and the clause still remains same. You can unlock this using these quantifiers, and if they are all unlocked, you can pass through it. This is now similar. So these are quantifier gadgets. Clause gadget, start, finish work same. Now a new gadget we have is quantifier gadget. So quantifier gadget is further subdivided into 2 classes. What do we call it? This,
Universal and existential.
this is called existential quantifier gadget and universal quantifier gadget. They work differently but can be built from a same piece, a same object. We'll explain what that object is. So a clause gadget again looks like this. You have 3 doors. If any one of them is open, you can pass through it. And opening a door is equivalent to setting L1 variable to true, or L2 variable to true, L3 variable to true, same as before. Here there are like a passage like this. Okay, Now we'll use a shorthand notation. This means plus A means you set A to true. You pressed a button, you press the button A. You are forced to press the button A. We will show how you will be forced to press the button A. And minus A means you were forced to press the button minus A, which means close the door. Plus A means open the door, we are forcing you to do that. Minus A means we are forcing you to close the door, A. Now each variable will correspond to only one door. So this meant open A, you can pass minus A, you cannot go back. So this is just like this. If you convert this to this, you go open it, you traverse it, you close it and pass away. This is a shorthand notation for a tunnel. Now we'll show using this tunnel type, using this shorthand notation and doors and buttons, we'll show how we can build existential quantifiers and these universal quantifiers, and we'll show what does this framework mean. We'll explain that again, just showing you how we can build these gadgets using these type of doors which can be forced open. So existential quantifier will work like this. You can either set all the x1 means first occurrence of x, x2 means second occurrence of x. You can set all the, you can close this door and you can go here, set all the occurrences of x as open, which means set x as to open all the occurrences of x, and then close all the occurrences of not of x, and then pass through here. This is an existential quantifier. You either set x to true or you set x to false. Similar to the way we check in TQFT, that you set it to any of the following, it should work. Now the universal quantifier works like this. You go through here, you first set x to true, you set it and set not of x to false. You move through here and then you come back. Also after passing through here, you come back, like this is how it works. You set everything to true, you come back. You set w to false and rest of these are still true, you come back. You check if you can satisfy this all. This is how the TQBF problem works. Similarly, like you check it for all w and there should exist a solution for z. For you check it for all y, there should exist a solution for x, and you keep on doing this. Set y to false, set to true, set to false, similar, and you this. So this is, you go forward, you set it to one of the following, you come back. This is universal quantifier works a bit different. You set x to true, move, go back, then you cannot pass here since d is here, right? So what you'll need to do is pass through here, set x as false, and then go through the whole pathway again, and then come, since d, you open d, come here. And this whenever you pass through here again, this whole gadget is reset since you essentially close this door. So this is how it works. You set to x to true, then set x to false, verify again, and then move. So using these two gadgets, I'll describe how the traversal works. I think I described it once. I'll describe it again. So we build these gadgets and we come at start point. We set x, there exists x as any of the following, since we have to show that for any true or for x can be true or false, this should be true for every possible thing. So we set x to true or false, and then we go, and then we set y to true, since we have to check it for both the trials. Then we set z to either true or false, whatever we think is, whatever has a solution, since we are verifying, as we showed that NP space is equivalent to P space. Then we set w as true. We check if all the clauses are satisfied. If they are not satisfied, since we are verifying a solution, then you immediately know there is no, this solution is wrong. You have to verify that the solution is correct. So you move through here, come back, you set w as false, you move through here again and set, you move through here, you set y as false, you set anything you like here, then you set this to again true, this to false, then you move through here, and if you are able to reach to finish, then you know that for this expression, this expression always evaluates to true, since you can build a solution for it. Now we'll show how using Celeste we will build this framework. Are there any doubts in this framework? Okay, I'll assume that's a no. So we only thing major we need to show is how to build the store. That's mainly all. We need to show how we'll force the person to open the door and how we'll force the person to close the door. And door we already have. Yeah. So door implementation. So using this force, we asked the modders community at Celeste, like, how do we force this button? We had no clue. So they said you can create a narrow passage and keep the button as it's inflated, it's pushed outwards. So it's pushed outwards and there is no pathway until you dash into it and go down. So you have to activate the button and you'll be able to move forward only then. So using this, we build that open traverse close pathway. You open the door, you are forced to open the door, otherwise you cannot move forward. You move, and then you can close, you have to close the door again. Something similar to this, we can keep this open pathway anywhere, we can keep this closed pathway anywhere. So this is how we'll build this notation. We can build plus x1, we can force them to using these narrow passages. uh, this is just to show that how we can club them together. Like, we come through here, we force them to set, since there were a bunch of these together, just set it as minus, say close this, close this, close this, close this. And this is how we build these kind of tunnels. Since we only needed the door gadget to build universal quantifier gadgets, these type of gadget, clause gadget, we can build, just have to place 3 doors. Thus we have built these gadgets, and using Celeste we have built this framework, and we have shown that you can reduce the TQFPF problem to this framework. uh, Thus this Celeste is PSPACE hard. Also, since in the we have to also show that Celeste is PSPACE. I think I missed the slide. Okay. For PSPACE, to show that this is in PSPACE, we can just show that here is a solution. You can traverse in these this pathway. No.
The number of frames remain polynomial to the
Oh yeah,
number of
yeah. Sorry.
variables.
Yeah. So no, that was the reduction proof. Since we have a polynomial size verifier, we only needed to show that, right? We have a polynomial size verifier using Celeste. We built a polynomial reduction that uh, for a there exists quantifier, we used only a polynomial amount of frames, and for the universal quantifier, we also use polynomial amount of frames. Since we have a polynomial size verifier, we can verify it in polynomial size, and in time does not, we do not care about time here. So it's PSPACE as well as PSPACE hard. Thus this modified Celeste is PSPACE complete. So we just wanted to talk a bit about what exactly changed. So before, when we did not add a close button, we had a thing that once we open a button, open a door, it was always open. So we could say that between the x door and the x plus 1th door, you always have a polynomial polynomial size, polynomial a pathway that takes polynomial time. Now, since we can close those buttons also, we do not have that. So the problem does not remain in NP, assuming that NP is unequal to.
The traversal is
Yeah,
not in NP.
it's not in NP. There is we do not have that proof.
Since we are repeating variables.
Since we needed to now store which states are also open, which buttons are open. Before we knew if we are at the X, then all the previous doors are open. So this just was the change that modified and put it out of, it made the problem more hard. So this is in the modified Celeste, we showed that it is PSPACE-complete. Thank you for joining. Any doubts?
Yeah. Are there any questions? Okay. I had one. So
Yeah.
seems like Celeste actually has a lot more game mechanics than you used to build your gadgets, right?
Yes.
So, like, let's say one of the mechanics that you used to build the gadgets was removed. it could still remain NP complete, or yeah, it could possibly become
It
simpler.
may it may if we add more gadgets, then we may not be able to show that it is an NP, but in our model it is in NP. We
No, not gadgets. I'm not talking
uh,
about gadgets.
yeah,
Gadgets, it's your proof choice, right?
yes, yes,
I'm talking more about the game mechanics. So basically, you proved its NP hardness by just using a subset of the game's features. Like,
yeah.
did you analyze like uh, whether there are any critical features in the game, critical game mechanics that force NP hardness?
Uh,
Like,
Zeeshan?
in the sense, if you
In the
remove like
sense,
half of these game mechanics that you used, but kept the remaining ones that you didn't actually use for the proof, maybe you can rewrite your proof to again show its NP hard by rephrasing your like gadgets, or using any other proof strategy of your choice.
you mean like instead of using the objects we used here, we use
Yeah,
some other gadgets?
yeah,
Yeah, so the thing is, the game has a lot of one-way traps. That is, if you do something, it'll stop you from going back or redoing it unless you start the level from the starting. So this was purely by choice, but there are a lot of other mechanisms. Like there is a key door, that is, you need to get a key to open the door. You can use that also as an OR
But
clause.
most of them can be like the key door can be modeled as a door again. So most of those gadgets are just the same, simply reducible to a combination or these gadgets only, which is why we do not really need to show that the key
These
door.
gadgets were out of choice. You can use, there are a lot of other sets of gadgets which you can use
yeah.
Yeah,
to
but
prove NP hardness.
they are reducible to these gadgets, as the key
That
door
wasn't
can be. Yeah.
that wasn't my question. I was more asking what subset of features, like if you had to
Oh,
pick the
okay.
largest subset of features that the problem fails to be NP complete, like drop the least number of features, like the so-called like critical hardness features,
Yeah.
like
You're
so
talking about
build the
like
analysis around those.
generalizations in such like if you have these properties, I can be sure that it is NP hard or something like that.
No, no,
Like
I
minimizing.
got it. It means like I think you drop some features and the problem stops becoming NP hard, right?
Yeah, exactly.
Oh, okay, okay.
We
So
haven't thought about that.
so in some sense those features would be the like true hardest features, right? Like that result in
Yeah,
the game's hardness.
Yeah,
So like
yeah.
yeah.
maybe there is some like analysis that can be done along those lines.
Yeah,
So
I think the Giovanni Vigilata paper, that thing analyzes a few of those aspects.
Okay,
You can, yeah.
Haven't checked yet.
Like in our original project, the last we added a few examples, sort of.
okay.
We'll check upon that, and if you find anything.
No, like I was curious because you went in one direction, right? You added features
Yeah,
that made it harder. So I was wondering like if you can subtract features and make it easier, and what would you choose to remove?
we haven't thought in that direction.
it will like
Still,
one-way traps that will be dropped. Like you do something, you cannot that cannot be redone until you start the level. That would be like the key features that make the game hard because you
Right.
cannot redo it.
So
yeah,
one-way trap even includes that platform
The,
that
yeah,
collapse.
that platform. There are other also, like there
Okay,
are a lot
okay,
of one-way traps like that.
right.
yeah. If you remove a one-way trap, then you cannot build a variable gadget, and this
Yeah,
strategy
yeah.
will fail. We do not know if there exists another.
Yeah,
Right,
basically the single use path is really, really important.
right. Nice. Yeah, the presentation was really nice, and yeah, like I actually understood like everything, which usually doesn't happen.
Nice.
Yeah. Does anyone else have any other questions they want to ask the speakers? Okay, so I'll be stopping the recording. You're free to like stay and like chat.